Hi, folks. Great to see everybody. One of these days we'll be back in person. All right, we'll get started right away. So our speaker today is David Duvenaud. David is most importantly a faculty affiliate at Schwartz Reisman. He's an assistant professor of computer science and statistics at U of T and holds a Canada Research Chair in Generative Models and also a you're still vector faculty, aren't you?
Yeah.
David? Yeah. So we wouldn't want to overlook that. He focuses on continuous time models, latent variable models, and deep learning. Postdoc was at Harvard, PhD at University of Cambridge, undergrad at University of Manitoba, and co-founded Invenia, an energy forecasting and trading company, and is also busy producing lots of children, one of whom will arrive any day. But we're it's okay if we have to call a halt to the session, David. Anyway, we're really looking forward to this talk on explaining decisions by generating counterfactuals. So we'll let you get started. Thanks, David.
Wonderful. Yeah, it's fun to be giving a talk to this audience. And I want to say, I think this talk's going to be a nice mix of sort of semi-philosophical questions and also, fun technical tools that help us maybe, in principle, automate some of these answers. We'll see. But I am challenged by giving a talk to such a diverse set of backgrounds. So please interrupt me. I'm definitely going to skip over explaining a word or an acronym or something. The talk is for you. Please interrupt me and ask me to elaborate. So most of this work was done over the last 2 years with my collaborators at the Vector Institute and Sick Kids, and that came in the 2 papers that were linked. Okay, so the whole point of all of this work came from the question of asking what is an explanation, and this came up a lot because now it's a hot area. In particular, I was interviewing faculty candidates who were doing their expertise was user interfaces and explainability, and they're saying this is the future, and I'd say okay, so just to warm up, what is an explanation? And I couldn't get a good answer from anybody, including people who had worked on this for years. And I'm almost certain that I looked around. I don't have much background in philosophy. I would love it if anyone would point to someone who's actually has what they think is a good treatment of these issues. But as far as I can tell, in human language or English language, an explanation, I claim, is something that, if it had been different, would have changed the answer to the question. So specifically, I'm saying, if I ask why was this thing true, I can automatically translate that into another equivalent sentence that is a what question. What, if it had been different, would have made X not true? If anyone thinks this is a silly question or a silly way of approaching it, please say something now, right? I think I have answers to all the common objections. So I'd love to hear any objections you guys have. And just as a concrete example, if someone says, hey, doctor, why do you think that this brain has a tumor? They could point to, for instance, this part of the image and say, if it had been different, I wouldn't have said there was a tumor. Right? So that's an explanation. So there's 2 things that jump out at us right away. One is there's many possible explanations for any question. And 2, probably some of them are sort of better than others in terms of being plausible or useful or actionable. So the claim of this talk is I'm going to hope to demonstrate to you that generative models, like these new probabilistic, deep, huge models like GANs that can generate images or text and do this sort of thing, can help us automate the process of generating and prioritizing plausible alternatives. And this is going to help in a whole bunch of different related questions. And I'm certainly not the only person claiming this or working in this area. I think this is maybe not even controversial now. I think 2 years ago it maybe was underappreciated, but the point is I'm not like some lone wolf trying to push this agenda here. Okay, so we have this new ability as of, let's say, 1 year ago, to do plausible in-painting or conditional generation. And so it's to be specific. So here's just an image of a bedroom. Now imagine I had only showed you this weirdly shaped subset, right? You're looking at this bedroom through some weird window or something. And the point is we can imagine all sorts of plausible completions of this image. And until really like a year ago, or even earlier this year, we knew it was possible, but we didn't actually have the tools to sample from that distribution of plausible infills. So here are a few possible infills, or rather completions of this image, that all share that same central tree shape. Actually, I'm just going to show this again. So here's the original image. That's an actual picture. We're only going to condition on this part. And now using deep generative models, here are three completely different but plausible alternative things we could have seen in that region of the image. So just to formalize what the ability we have now is we can sample from this distribution of one part of the image given the other part. And it doesn't really matter which part you're even looking at anymore. And so, yeah, so we can automatically consider plausible alternatives in any part of the image, or, in parts of text documents, or any sort of, joint data that we might want to consider. So any questions so far? Okay, well, this might seem like easy, but, when I joined the field, we couldn't even generate blurry, tiny 10 by 10 images. And this, in fact, we started this project before this thing was available. So our infills aren't quite as impressive in the stuff I'm going to show you. Okay. So one thing I want everyone to know, even if they're not interested in explainability, is that this means we can pretty much handle missing data automatically now, in a very automatic and general way. And other people who are sort of Bayesians have been saying similar things for years. It's only recently become practical. So here's a paper from one of my old advisors saying, yeah, if I have a database with a bunch of columns and some of them happen to be missing, you should absolutely not just like fill them in with the average or somehow say like not applicable. You should, what instead you should do is build a joint probability distribution over all the different entries in a row, condition on the ones that you do see, and then average over all the plausible things that could have been in the columns that you didn't happen to record. So I'm not sure if there's anything controversial here, but I don't think everyone appreciates that there actually is a, I think, completely satisfying answer to how to deal with missing or even like corrupted or messy data. Obviously, this won't work as well if the data you do have is ambiguous about the data that you don't have. But well, we can't do magic. Okay. Anyway, I would love it if there's a question here, even someone who thinks, especially if someone thinks this whole thing is stupid, it's much more fun to give a talk that's more of a discussion.
So let me just, so your claim that it's easy, that there's an easy solution, surely that depends on how much is missing and how much you have.
Well, I'm saying the setting up the technical infrastructure to average over the missing parts is equally hard, no matter how much is missing, but that the answer will be worse, or rather the answer will be more indeterminate the more data is missing.
Right. Okay, and that indeterminacy is going to show up in your confidence in your predictions.
Yeah, exactly. And when things are indeterminate is really the only time when you have to sort of consider all possibilities. If one of the columns is completely determined by the others, then we can just use our best guess and that'll work fine. It's only when there's some ambiguity, and particularly like jointly over a bunch of different fields, that it's important to consider their joint distribution. A good example would be, if we see a document that says something happened in Cambridge, you're not sure if it happened in Cambridge, England, Cambridge, Ontario, Cambridge, Massachusetts, and all of the other missing data will be like highly correlated, but also completely distinct depending on those three, which one of those three possibilities we're in. So confidently just choosing one and filling in all the data is going to lead to disaster at least some of the time. Great, thank you for the question, Jillian. Okay, so now I'm going to say we can use these tools we have to basically fill in the blanks of that definition I gave earlier. So the sort of explanation that I'm going to focus on explaining in the first part of the talk is image classifiers. And then in the later part of the talk, I'm going to talk about an application to health data, like medical records. So the images are much easier to understand what's going on though, and we can't really like show you real medical data, so it all has to be simulated, so it's not as fun to look at. So the idea is here that we're going to have a neural network that takes in some image and outputs a distribution over what class of object it is. And usually there's like 100 or 1,000 classes, like is it a boat or a toy or a cat or a dog or whatever. So we're just going to get this 1,000 numbers that add up to 1 that tells us how much the neural network thinks it's each of these classes. It's obviously going to be applied to like medical diagnosis or whatever. Oops. Okay, so I'm going to say that the basic things you need in this recipe that I'm going to give are some sort of automatic answer giver, like something that gives P of class given image, like our neural network, or even in principle, like a person. And then the other thing we'll need is an automatic source of plausible counterfactuals, which is equivalent to having a joint distribution over all the pixels in images. If you have that, that is enough to let you compute or sample from, this distribution of what is, for instance, the top half of the image given the bottom half. Or as I mentioned before, like the edge of the image given the center. Once you have this joint distribution over all possible pixels, you can answer any one of these questions automatically, just using the rules of probability and conditioning. And so specifically, with these two tools, I can ask and answer the question, what about this image, had it been different, would have changed the classifier's answer? Right. Okay. Any questions about this roadmap? Cool. And again, obviously there's many, like for instance, if this neural network said, oh, here's a raccoon, there's many different things that I could change about the image that would make me not think it's a raccoon anymore, right? Again, this is under-specified, but that's sort of okay. Okay, and now this is going to be like the mathiest part of the talk. I just want to cover the history of attempts, or like how we got here, right? So again, I'm not like some lone wolf saying this is the way we should do things. And the earliest image explainers, I claim retroactively, were doing the same thing that I'm doing now. So until like a year or two ago, the name of the game for explaining neural network decisions was something called Saliency Maps, which what they are is just a plot of the gradient of the class probability of the classifier with respect to all the pixels. And so, sorry, this is a little bit of notation, but the idea is just to show you visually, if I took an image of a sailboat, showed it to a classifier, and plotted how much would changing each pixel, making it brighter or darker, change the output of my classifier, I can just plot that as an image. And I get something that maybe sort of, you can see the boat in there, maybe the water. It's not, it didn't really work all that well, right? But it was like, this was the beginning of this whole field. And, yeah, so what the question that it answers is, which direction of changing all the pixels would most change the label, right? So I'm retroactively claiming that these were forerunners to the approach that I'm advocating, which is that the definition of derivatives is actually a counterfactual, and that here's the definition of derivative for any function, and it just says, evaluate the function at one location, x, evaluate it at a slightly different location, and ask how much that changes the output. So I thought that was a nice connection when, when I realized, yeah, we can think of gradients or derivatives as just instantaneous counterfactuals. Okay. But I think everyone agrees they don't really work all that well. And I would say they're asking the wrong question. This question of what direction can I move the pixels, that's kind of weird, because the images that have all their pixels modified a little bit by these sort of noisy images aren't really images we would expect to normally see. So what we would like to, and again, here's some more examples of, here's a stethoscope, and their saliency map doesn't really focus on it. And so what everyone's been trying to do since then is to somehow restrict ourselves to the manifold of plausible images. So to say, what direction can I move my image in such that it's still a normal image that looks like something, but would also change the image or the class label. Okay. Okay, and so, some of the refinements that were made were to say, okay, let's make sure that the images are somehow still smooth. So for instance, we'll consider taking the original image and ask which parts of it could I blur? And, that would most change the class label. And then, blurry images are still something you might sort of see. And so this was a 2017 paper saying, okay, I found that if I just blur this part of the image, then now my image classifier went from being totally sure that 99% sure that it's a flute to totally sure that it's not a flute. So this mask, this area, this region is my explanation for why this image was classified as having a flute. And this certainly looks a lot better than the sort of noisy nonsense that we saw on the previous page. Okay. And then other people said, well, let's not just blur because the information still comes through. Let's just replace it with some sort of like background noise or something like some snow or some static. So another contemporaneous paper asked, okay, which parts of the image, if replaced with noise, would least change the class label? So these are still like implausible, but anyway, these are just things that people are trying, and it seems to work pretty well. But there's like I would say a fundamental problem with all of these things, which is that when you start somehow like masking the image or covering up part of the image, it's not what the classifier has been trained on, and it's not clear if the network knows that you're asking it like this part is somehow censored, or if it thinks that there's actually a black box there in that part of the image, right? Like if I showed you this image, it's actually kind of ambiguous whether I'm trying to say this was not recorded or there's actually this black cube in this guy's brain. So we have two ways forward. One is we can build a classifier that has a special sort of mask input. Like we can have a special color. That means we did not record this, right? And that happens all the time when we have forms. It's like missing or not applicable or something. And then you have to retrain the network on all possible ways that you could have censored the data. So that's expensive, but it's certainly something you can do, and people do it. And then, but I'm going to propose we do a second approach, which is much more flexible, which is that I'm going to say, I have a classifier that can only take whole images. So I'm going to fill in these blank parts with one of these like generative models conditioned on the rest of the image, show it a whole bunch of different possible completions, and then average the class probabilities over all those image completions. So this is slow because now I have to sample a bunch of completions and then show each one to the classifier separately, but it works for any classifier and I don't have to retrain it. Okay, any questions again?
Yeah, can I ask you on this one, David, because this is what I was wondering with that missing data point earlier. So if I have an outlier, which I sort of think that tumor is an outlier, right? How am I ever going to fill in an outlier by averaging across all the non-outlier data?
Oh, yeah, great question. So I say that in principle, the right answer is to fill in according to what you would expect to see given all the data that you know about this particular person or patient or circumstance. So you're right. If let's say only 1% of people have tumors in this area, then only 1% of my completions should have a tumor here. But we should definitely include those because, again, I'm not saying we should fill in with the most likely patch. I'm saying we should average over all possibilities proportional to how often we would expect to see them in real life. And that includes outliers. Oh, and Sheila, you just shut up. I think you'd please re-explain anything that I'm butchering.
No. I have a different question, which is related to Jillian's question, or perhaps Jillian's intuitions, which is that often, so another view of explanation is that there's some discrepancy between what, for example, you as a human being would predict would be the outcome and what you're actually seeing. And that discrepancy between what you predict and what you actually see is what precipitates the need for an explanation. So you're looking for an explanation. And in that regard, to sort of Jillian's point, perhaps, if you have often you have great models for normal behavior. tons and tons of images of brains that look perfectly healthy. And then how do you account for a discrepancy when the discrepancy is not part of the generative model?
I see. So you're right. I don't think we can. I think if our generative model hasn't been trained on a big enough or diverse enough data set such that it can't imagine seeing such an outlier, it won't propose it. And that would just make the system work worse. So all of this, the answers that this system gives will only be as good as the generative model is faithful to the real world.
Right.
And that's why I'm sort of giving this talk now, is because we didn't have good enough generative models to even plausibly capture the real world until just like a year or two ago.
And so maybe part of the way forward is if one understands the normal behavior, you have a generative model, but you understand the causal relationships between things, and you can understand how something not working could manifest in the absence of some particular element that might explain, that might account for what you're observing. Anyway,
No, so actually I'm going to talk about that at the end, that explaining things in terms of pixels in an image is a very poor, very impoverished language for answering a question. And we would rather say things more about like, oh, because this happened to them when they were a kid, or they had this gene, or something more abstract. And I absolutely think we should move in that direction. And this is just baby steps. Okay.
Thank you for the interest.
Oh. All right. Yeah, so the question that I'm saying we should ask is, what region of this image, had it not been seen, would most have changed the classification? I'm saying this would be a good way to find, at least point a human to a part of the image that says, this is the reason why this classifier made its decision. That's not always like a useful thing, but I'm saying it's more useful than like saliency maps. Ultimately, if we have a real application, I would want to know, what decision are you going to be making based on this? And we probably could come up with some more like specific question to ask. But I'm claiming that no matter what question you ask, probably you're going to want to average over possible things that you could have seen but didn't. And this is just one such question. If you guys think of some more specific question you'd like to ask about like an image, just tell me, and if we try to rephrase it into this language, I bet it will require these sampling plausible counterfactuals. Okay, and then just if someone's really curious about notation, we're going to ask, what is the class probability given the image X with this /r means with some region removed, and just the rules of probability. This is always true. That's equivalent to summing over all possible entire images, or rather completions of the image, condition on the parts that we do know, and then sending that to the classifier. So this is just saying that, you have to average the class probabilities to find out what you would have expected to see. Okay. Right, and so to give another, just to contrast the old approaches and the new approach, we can imagine here's an image of a bird, the classifier is confident. We can imagine saying, okay, I'm just going to see if this region is important by blurring it. And in this instance, the classifier still sort of thinks there's a bird. We could add random noise, or here's our conditional infiller, which, it's funny, here the model didn't actually notice, this head is probably enough to fill in a bird. And in this image, I have to say, we were still using like much more primitive versions of these image infillers back in 2019 when we did this work. So it didn't actually notice that, and it just filled in the sort of forest background in this region. But the point is, this is like a plausible infill, and the model still thinks there could be a bird based on this head. It's not sure. Okay, so the only step left in the approach that I'm proposing is, now we have to find a mask, like choose which region we're going to censor. And again, we're trying to find the mask that says large. Oh, well, the blue parts are the parts that are masked out here. We're saying fill in, or like mask out as much as you can, such that when you fill things in, you don't change the class probabilities much. So there's this, we have to weigh how much we care about the mask being large versus how much we care about changing the class probabilities. But you can see, actually, sorry, here I did it the other way. Conditioned on this part of the image, here's what the infiller filled in for the rest. Okay, so I actually just, there's another point that I wanted to make, which is that there's actually two ways to set this up. One is to find the part of the image that if you blocked it and then filled it in, you would still fill in something roughly similar and get the same class label. The other one to ask is, which part of the image, if I block everything, or if I mask out everything else and fill it in, will change the class labels. So anyway, I think these are roughly equivalent. Anyway, that's not an important detail, but I just realized I might have confused you guys by mixing it up when I was explaining it here. Okay, so anyway, the main algorithm here involves choosing the shape of a mask, sampling the parts that are masked out, sending it to a classifier, and then adjusting it to, hopefully, again, be as maybe as small as possible while still having the same class probability. Okay, any questions about like what the algorithm actually is, what it inputs, what it outputs? The input is an image and the output is a mask. And the claim is that this mask is the part of the image that explains why that image had the class probability that it did.
Tegan has a question in the chat. Tegan, do you want to do it verbally?
Oh, sure. It's more of a comment than a question. I guess I can turn it into a question by saying this is sort of in response to the conversation you and Sheila were having about, I would summarize it maybe as extrapolation, model extrapolation, like the ability to represent modes that are maybe covered by combinations of features in the training data, but not, explicitly, let's say in pixel space represented in the training data. And I mentioned manifold mix-up from Alex Lam. I guess, so turning it into a question, what do you think of methods like that? How well would you compare it with what methods you're talking about?
Oh, sure. I guess I would say what I'm proposing here is orthogonal to which generative model you happen to be using, right? And I'm saying it doesn't matter, just plug in whatever one works best. Whatever the one that's best changes every few months right now anyways. And we would hope that they would be able to generalize in a strong way. And the better they generalize, the better this thing is going to work.
I guess the very interesting thing would, and I haven't thought about this very hard, if there's a way that this could interact.
Oh, I think you muffled your mic right there.
Oh, sorry about that. How's that?
Yeah, now I can hear you.
Cool. It would be very.
Oh, no, you're muffled.
Okay, I'll type it. It's sort of a comment.
Okay, I'll keep my eye on the chat. Cool. Okay, and then very quickly, like I would say this worked. So comparing against the old baselines, here's some penguins. If we tried to find the mask according to the same procedure, but blurring instead of infilling, we get this crazy stuff. But our approach finds the penguins. Same with the golf ball. Same with the butterflies. It's kind of a funny question because usually you don't need the whole object to identify like what type of class something is. So I think often the masks are smaller than people expect. And I guess the point is we're not asking to outline the object. We're asking, again, which part of the image is enough for you to know that it's a butterfly if you only saw that part. And I guess, these neural networks become like experts, what's the word for insectologist? So maybe they can tell what kind of thing it is just looking at the head and the antenna and stuff like that. Entomologist, thank you. And Tegan asks, is it completely orthogonal to choice of generative model? Well, yeah, some would interact beneficially. Yeah, so I guess I'll say some will certainly work better on some tasks than others. I'm trying to say the overall recipe is agnostic to which generative model you're using. Okay, and as I mentioned, there's this caveat, which is there's this sparsity penalty that says how much do we care about keeping the class probability the same versus how small the mask is. And so if you, on one end, it'll choose really, really small masks that also let the class probabilities change a lot. On the other end, they'll basically say, you need to see the whole image to be exactly as sure as you used to be about what class is. And there's no real principled way to trade that off without knowing sort of what you're using these masks for. And that's sort of true of almost every one of these methods. Okay, Yeah, and again, here, I'm trying to buttress my claim that it doesn't matter which generative model you use very much. And so here is sort of like two different generative models that fill things in. Also, here's using like local, just like sort of like a local averaging approach. And they give like roughly similar answers, and better than the sort of more naive approaches, right? Okay, so that how well this method actually works, I don't think is that important, because again, the underlying tools have already moved on. One thing I'll say is it's very hard to actually evaluate these methods because, again, without a concrete task in mind, it's kind of hard to say what the right answer is. So for all these papers, we just inherited this way of measuring progress, which is choose a task where we're going to define like these are the real pixels that actually matter, just by some domain expert. And then we ask, how well does the computer match the region that the expert said was the important one? And so, this one happens to be able to find smaller masks, or rather, let's say the percentage of the mask, the true masks that are included in ours, in a way that accounts for how big it is, was better than the previous approaches. All right, so obviously this is like very ramshackle prototype proof of concept stuff. And so there's obviously a few technical limitations here of like, we need better generative models, which, or I guess now we should have used, or we can rerun this with those now. This is a little bit slow because we have to do that sampling of those conditional infills. And optimizing the shape of the mass region is kind of hard. And we end up with these sort of like little disconnected regions. Probably we want to say like that it's some big contiguous shape. But I think what's more, what's more interesting to this crowd is like the conceptual limitations, right? Are we even asking the right question? So certainly we should be offering, whenever we answer the question why, we should be willing to offer multiple possible explanations. And that's sort of technically straightforward. We can just rerun our optimizer from different random restarts or something like that. We would certainly like our explanations to relate to actions that can be taken by the user. Right, like it doesn't matter if you said, oh, if this person had completely different genes, they wouldn't have this tumor. It's like, well, it's too late, right? Like, and then I really want to be able to move beyond parts of images as a tool for like explanation, right? We started there with this kind of where the field was 2 years ago, but I think no one's going to be satisfied with this. One good counterexample I think of is, this saying that sailors have, it's like red night in the morning, sailors take warning, red night at light, or red sky at night, sailors delight. If you try to explain that classifier on this using this method, it would just highlight, I guess, either like one pixel of the sky or like the entire sky, and just say like, that's why I think it's going to rain or there's going to be a storm. It doesn't actually tell you, well, like what exactly in that sky made you think that. So we definitely would want to give answers in terms of some sort of like higher level explanations, and that's super wide open and super hard. I'm going to talk a little bit about now some work that's not done by me that is moving in this direction, but I'd love if you guys have any thoughts on how to address any of these conceptual limitations.
David, I think we're going to have lots of conversation about the conceptual piece when we get, so I would suggest we hang on to those. Certainly, I have lots to say about that.
Okay, great.
I know others do.
Great. Yeah, so just some other refinements I want to mention. There's two ways to set this up. I already said this before. You can try to find the smallest sufficient region, such like the smallest region that allows a confident classification, or the smallest destroying region, which is the smallest region that if you removed it would stop you from confidently classifying. And so this is again from Yaron Gal. Here's an image. Here's a region that is sufficient to tell that it's some seals. And then here is, we're saying, if you destroyed this region, I wouldn't know that it was a seal. And I think an interesting open technical question is there a sense in which these are equivalent, right? Like the exact answer that we find here depends on our generative model and optimization procedure and a few things. But if we had, let's say, like perfect generative models, exact optimization, I think there might be conditions under which these are equivalent, and that would be a fun technical result. I would love to chat with any of you about it if you're interested. Okay, and then now I want to say this higher level counterfactuals thing is something that I think is also like pretty much almost enabled by generative models. And so this is actually still, it's like 2 years old, right? That's like so ancient now. This guy, David Duvenaud, he looked at generative models of images. So these are all images that are, oh, right. Yeah, I think these are all generated by GANs. And what he did is he went into these pre-trained GANs and found hidden units that corresponded to things that we humans already have words for, like people, trees, buildings, grass, whatever. And then so he can just go and say, okay, take that unit and then set its activation to 0 or 1 or whatever. And then he can like add or remove trees. It's like this very generic photo editing ability. So here he has an image that was generated. Then he turns off the person units and he gets a very similar image, but without the humans. And it's not like the humans are just like, you know, blacked out. They're actually filled in with sort of plausible counterfactuals. Of course, this is again using like 2 years old GANs, which look terrible. I bet there's better ones that we could have done today. So yeah, here he gets rid of the windows. Here he gets rid of the table units, and the table just gets smaller, right? So it's not it's not a exact science, but the point is it's certainly possible. Okay, and now I'm going to try to, you know, not just talk about images, but try to relate this more concretely to some health application. And this was joint work with Anna Goldenberg, Sana Tony Carboni, and Shamali Joshi, who all have like health backgrounds. And we thought, okay, well, let's actually apply it in the proof of concept way to health. And so the questions that we were hoping we could answer was like, in the specific context of like, this patient had these measurements and this risk model is like changing its prediction that they're gonna like die or whatever over time. We might want to ask, okay, so what exactly about this data made the classifier change its risk assessment? Or like a more concrete question is, this doctor just came on shift. There's like a huge ream of data. Everything's changed. How are you going to prioritize what to show to the doctor so that they get up to speed without having to read the entire chart from end to end, or like look at the entire like EEG or whatever? So I think I'm claiming that we can use these tools to answer these questions. And, you know, again, the first step is turn this question into a slightly more technical, well-defined question. So here we can, so for instance, we could ask, if you had all this data, and this is what time it is. So you have like 4 different data points that you want to gauge their importance somehow. If you had to choose one, you could ask which one data point would most change my predictive distribution. For instance, you can come up with situations where that's not actually good though, because it might change the prediction in the wrong way. So we sort of played around with it. We thought of a whole bunch of different, more like technical objectives we could try to satisfy that would be like realistically useful. The best one we could come up with in general was this one, feature importance in time, which tries to minimize the divergence between 2 distributions. One of them says, I see all the data. That's what I mean by P of Y given X 0 to T. The other one says, I saw all the data before today and a subset of today's data. And the idea is that we want to choose the subset of today's data that if you saw it would put your state of mind most closely to that if you had seen all of the data, right? The idea is that we would like to show the doctor all the data, but we don't have time. So we're going to ask what subset would make him or her come to the right conclusion, like in terms of what probability distribution over outcomes they believe. So I think that's a pretty good thing to optimize. It's like, obviously it depends on the application. I'm not going to like say that there aren't better ones in different situations. But what I will say is, I think I have it on the next slide. Right. So many different possible metrics. But the point that I want to make is that any of them that require integrating over the data that you didn't see requires you to use some sort of generative probabilistic model. And for those who haven't seen scale, that's called a Kleibler divergence, and it's also an average over all the data that you didn't see. So, and then, I can't show you fun image completions because it's like medical data. So all we did for this, or for how we validated the model in this setting, was we made up a fake physiology rules where the patient's state changes from time to time. And there's sort of ambiguous markers of that change of state. And so when the color here changes, that means that the patient's state changed on this like made up example. And then our feature importance through time score spikes when that changes, right? And the point is, this was important data to maybe have shown someone who cares about this patient. And it explains why, or what data most changed the model's predictions.
David?
Yep.
I was just actually going to ping Laura Rosella to say, what does this look like to you, Laura? And she threw that question in the chat. So Laura, I want you.
Yeah. So my question was, so what's the decision, like what's the doctor doing once you show them this? Is it to understand the model better so that they could be more confident using it? Or are they actually taking this piece of information that you're showing them and expected to make a decision on it?
Great question. So I would say both. Like, I am interested in the ultimate use case where the doctor is making decisions based on this data, but more realistically, my health collaborators were saying that's like decades away or whatever. Let's just focus on helping the doctor gain trust in the model so that they might, use its summary output or something like that. So the point is that I think this would help in both situations.
Yeah, I guess because on the latter, the first one makes a lot of sense. And I think the latter, the challenge is something might pop up because that's what's measured, but that's actually not the issue. Some biomarker might light up, but the clinical decision action has to be taken on something else that's not measured by that's popping up, right?
That might be right. I do think that is actually covered in this metric because it depends on how expansively you define this like Y thing. If this Y is sort of like everything that's relevant to the patient's health and treatment, then what this is saying is I'm going to show the doctor the subset of the data that would make their opinion be the same or as close to the same as possible to if they had seen all the data, which should include that clinically relevant data that you mentioned might not be in the subset that we actually show them.
Right.
It's kind of funny because you can imagine telling someone a lie that makes them believe that the actual true thing and then getting into all sorts of trouble down the road. Like, I definitely think there are like issues with this, and I don't want to like put this into practice. And the main thing is also, if we don't believe the model, right, we can't actually compute what the doctor would believe if they saw all the data. We can only ask what the model would believe if it saw all the data. And if the doctor has access to side information or the model is bad or whatever, that's not going to be a good match.
Right. Okay, great. Thank you.
Oh, thank you. Oh, and Vipul asks a question. Are we trying to find a continuous subset of the time series? What about the non-continuous but repeating parts of the time series? So that's a great question. I think that if there is a repeating signal, you should only need to show the doctor enough of the repetitions so that they're sure it does actually repeat. And then it might not matter which ones you show them. Yeah, so again, the nice thing about this is that you never have to laboriously show the doctor every single piece of evidence that all matches the same conclusion. You only need to show enough that they can come to that conclusion on their own. I hope that answers your question. But I'm almost done, so I'll just get to the end of my slides and then we can have a longer free-form discussion. Okay, so, and I just want to mention, like there's lots of alternatives. Most of them use these gradients, which I would say are like instantaneous counterfactuals, or fill in the missing data with averages. Of course, there's code for all this. It's available. And then again, I want to make more, when I was saying I'm not the only one doing this, I want to make that more concrete. So I don't know if you guys have ever heard of like Shapley values. They're another way of, it's very similar to what we were talking about before with the gradients, is like assigning importance to features. And it's done in a like non-image setting. And they usually end up somehow integrating over the unseen features by just sampling relevant or sampling values for that column that just appeared, but like randomly sampled from the data set. So not in any coherent joint way. So if I was doing this with images, it would basically just look like I was sampling static, because I would sample every pixel independently. So concurrent to the first paper we did, there was a paper, this one, explaining individual predictions when features are dependent, more accurate approximations to Shapley values, that basically had the exact same thesis that we did, but in a non-image setting, and said, let's build big probabilistic models. And then when we infill, we'll sample coherent like stories that, or rather samples from a joint distribution. And people call this like conditional Shapley. And I think it's absolutely just better than standard Shapley for the reasons that I outlined for this whole talk. And then there's a cool paper that just came out last year, causal Shapley values, which says, well, sometimes I might ask the question, not what if I see this particular feature, but what if I actually force it to be that way? So a good example would be like, if you see someone's bone is like in the right spot, great. If their arm is broken and you just like force the bones back together, that actually doesn't mean that they're okay. And well, that's, okay, a better example is if I see that someone has yellow teeth, I might think they're smokers and thus have cancer, but me just like whitening their teeth won't address the cancer, right? So people are trying to extend these explanations to that situation, but everything that has been done so far requires you to somehow know the causal relationships between the features, which is, I would say, kind of the question we're trying to answer most of the time when we enter one of these problems. But this is just to, like, for anyone who wants to go in further, these are some of the like interesting directions that the field is going, and also to make it clear, I'm not like the only one doing this. So the takeaways from all of this, I would say, are that conditional generative models are like newly powerful as of like this year, and let us automatically reason about counterfactuals. And then figuring out what question to ask these models is usually the hard part. So I'd like to thank you, my collaborators, and thank you for hosting me today.
Great. Thanks, David. You want to stop the share and we'll see everybody here?
Sure.
There we go. Excellent. Okay, wonderful. Thanks very much. Peter, do you want to jump in? I know you.
Yeah, I'm happy to kick it off. First of all, to say thanks very much to David. I just want to note for accuracy here that Jillian mentioned every place that David has been and worked except for UBC. He did his graduate degree, which is where David and I lived together in college. So we've gone back a long way. So it's been like 13 years. David's been making me feel like my brain doesn't work very well. So thanks, David. That was really great. I wanted to ask you a question to go all the way kind of back to the first slide and just ask you to reflect a little bit on explanations. And I'll tell you that I come at this from a couple of perspectives. One is kind of the perspective of having interest in causal inference, which is largely about, trying to discipline the way we think about counterfactuals in a way that allows us to actually, identify explanations or causes of things. But the other one is a more kind of just a general question on definitions, which is whether we're really talking about something like explanations here, or talking about things like essences. And I'll just articulate it in the following way: that what this seems to be really good at doing, especially if we think about it as images, is that it's telling us what elements are most essential to making something, right? This is kind of like what is it about the image that has the most power in telling you that the dog is a dog, as opposed to something else, right? And I think that's for me, that seems to be a very powerful way of thinking about this, particularly because so much of what we're interested in doing in the social sciences, at least, is actually classification, is taking sets of things and trying to figure out what actually is essential to their being what they are, right? As opposed to being something else. That was one sort of, so I wanted to ask whether this is about explanation or about essential things. And the other thing is just, for me, a very interesting feature of human explanation for things is that reason giving is often done in a way that is backward looking, that something happens and we try to come up with an explanation for it, but that explanation is partially about the actual objectives of what happened, but also partially about a person's own beliefs and the shared beliefs with the person that they're speaking with, right? So a doctor wouldn't take your definition of explanation as being sufficient, right? Because they'd have to think about their own explanation about why something happened with a patient would involve a really strong set of priors about what really matters, as opposed to kind of this form, which isn't rooted in belief, right? So I just wonder if you can kind of reflect on the degree to which, like what this means in a world where people are coming up with reasons for things that are not, essentially where their priors are not uniform, but they actually have beliefs about how something happens, and the explanations you identify may be more or less consonant with those beliefs. Also, good luck with the baby.
Thank you. Thank you very much. Yeah, thank you for those mind expanding questions. I had never heard either of them before. So for the essences thing, I guess I would say, I think you might be right, but I guess I would prefer to try to define essences in terms of explanations, because I think I can define explanations in terms of probabilities, and I definitely know what probabilities are. And I definitely don't know what an essence is. So I guess I'm trying to say the reason I like taking things in this direction is just because I want to ground things in terms of technical or as precise language as possible.
So I'm with you this far, actually. And I actually, just for what it's worth, before we go to the next part of the answer, I think this is actually pretty consistent in a backwards way with how we think about causal identification in a kind of a potential outcomes framework, right? That what we're trying to do is estimate the degree to which something mattered for an outcome, right? So I'm with you. I'm with you so far.
Okay, and then but beyond that, I think maybe if you could propose a stronger or a more precise definition for essence, I would love to try to like frame it in a similar way. But maybe we can come back to that. I want to answer your second question, which is that I had never thought about this before, but you're totally right that I was saying an explanation is relative to a probability distribution. You're totally right that everybody has their own probability distributions. So it's certainly the case that sometimes somebody has their own private explanation, and they know that because the other person has a different set of beliefs, that actually won't be a good explanation for them. And that's certainly like relevant in a clinical setting. And I just hadn't actually put that together until now. Thank you.
Okay, sorry, I lost my mute button there. Thanks, Peter. Thanks, David. That's great. Benjamin.
Yeah, thank you. I thought this is really fascinating. I'm worried about cases. So I'm trying to apply this to other sorts of cases that I worry about for explanation, where we're worried about bias and things like that. And those aren't usually image cases, so I might just screw this up because maybe I'll extend it wrong. But I'm worried about a case where you say you black out like race off of the data that you've got on someone because you want to check whether it's looking at that. But it turns out that most of the plausible infills infill the same race anyways because of surrounding data, or just things like that. And then it turns out your model tells you that race didn't matter very much, but that's only because it feels like that's what would happen on your model, because most of the infills are going to end up being identical to the masked data anyways. And in those kinds of cases, so it's one of these cases where the closest counterfactuals to the real world end up keeping the thing we care about steady, and thus don't test whether it's really serving as an explanation in the right kind of way. Does that make sense?
No, totally. And I guess I would say, have you ever guys heard the slogan, no counterfactual without intervention? And the point is we should only ask about things that we could have actually changed. And so a classic example I would say is like, imagine that I'm looking at a resume classifier and it says, oh, this woman is like not qualified or whatever. And then you say, oh, well, what if I just changed her gender to man? And then I think a good answer to that would be to say, well, it doesn't really matter what the classifier does when it sees a man who went to like a women's college and was on like women's sports teams or something that like didn't match and you had never seen in the training set. And so I think, I forget who talked about this in like the 70s, is like Rubin or someone was saying, we have to go back and imagine a specific counterfactual where this person's gametes were different, or rather their like chromosomes were different or some particular thing. So I think that would dissolve your objection, is to say, well, race didn't matter in that scenario, in the sense that if we didn't know what it was, but they still had all these markers, we would still make the same decision. But it might have mattered in the sense that if you had gone back and changed what race they were born as, whatever that means, like without like, it's not really clear what it means, but I think if you specified the intervention, it would dissolve your question.
Okay, well, I just worry then that, because it feels like that's one of the things we really want explanations for out of, or at least one of the things I want. Maybe I'm wanting something different than you out of explanations for these decisions, because some people, when people like in the GDPR, when they say you have a right to an explanation, it seems like partly that's because you're worried that it might be making decisions on irrelevant grounds, and often the irrelevant grounds are precisely the ones you can't change.
Sure. I mean, I think that's a valid concern. I guess I still don't think that the question is well enough specified. That's all.
Thanks.
Thank you.
Can I just insert myself in the conversation here? Because Benjamin and I have been thinking about explanation and justification for some time. And I do think it goes back to your original point, like what's an explanation for? What is an explanation? And I think this is a really big difference between the way we're thinking about explanations, like what you're presenting, sort of like from the point of view of understanding the way the model is working. Why is it predicting this classification and not this other one? Versus when we say, actually, I think the word explanation is used in a very different way, say in the GDPR, when people say, you know, people are entitled to an explanation for the model. They're actually, you know, they're saying, no, I want a justification, which is actually about offering reasons that are consistent with the set of things that people are allowed to say as a justifiable reason, and that changes from communities. And it's not about causal reasoning at all. It may be related to causal reasoning, but I think that's just going back to that starting point of what is an explanation. So you put up a definition, and I would say, well, yeah, that's a very specific understanding of explanation. In this, it's a causal explanation. Why did the model do this? Very different from, okay, explain to me why you didn't give me the job. Oh, and here's a reason you're not allowed to give. You know, you were the wrong race. I wasn't looking for somebody of your race. That's an inadmissible reason. So I think it's really important for this to be, and I think this is really critical because we don't want to send people down the path of producing methods of generating explanations, saying, hey, we're solving that problem that, like, the GDPR is telling us we need to solve. I think it's a very different thing.
I agree. I mean, I guess I would lean to say we shouldn't try to ask our machine to do one thing and then tell it you're not allowed to like answer that, right? Like, I mean, obviously we are going to sort of do that, but I guess I'm saying we're setting ourselves up for failure when we try that. But I don't know that much about these issues, so I don't want to spend too much time talking about it. I want to say thank you to Peter. It was, yeah, Holland and Ruben who raised this original point about interventions defining counterfactuals.
Great. Okay, thanks. Daniel.
Hey, yeah, also same comment about great talk. Really enjoyed it. I guess I just wanted to like make sure I'm understanding things correctly. And I think my first point was actually just, Jillian just touched on it, as kind of a semantic one about explanation as justification versus explanation as, you know, mechanistic mechanism, and explanation is like statistical probability. So, I mean, maybe you don't want to get into that anymore, but I just feel like I had the same kind of like question about like how exactly I should be thinking about explanation, and how exactly you're kind of like framing it in respect to those other kind of concepts. And then sorry, if you want to jump in, I can ask my second one.
I was just gonna say, I think I was being a very narrow-minded technical kind of guy and saying, I just want to give a descriptive explanation, not in terms of like justice or something like that.
Fair enough. And then the second one was just like, I'm trying to like, yeah, get a better understanding. Like, and I think that I'm like kind of going back to things that I do understand. And so I'm wondering, like, when you gave like the last example, like here's some kind of like information we have on a chart, and we're trying to figure out like what one is most informative about kind of like the diagnosis that the physician is coming up with, or with the algorithm is coming up with. Like, how should I think about that? Like, how is that different than just like feature weights in a regression? Like, how do I think about that differently?
Oh, it's almost the same question as feature weights in regression. And that's what all the Shapley stuff at the end was doing. And I was just focusing on the image version because, well, we have this thing where we want maybe like regions or something like that. And I think that's just because we want to talk about objects actually. But it's just because it's easier to understand, and it's much more enjoyable to talk if we have images to reason about.
Okay.
Thanks.
Thanks, Daniel. Thanks, David. Sheila.
Great talk, David. Thank you. Yeah, Jillian, maybe you can put down my hand. Thank you, or I'll do it. A couple of comments, I guess, spurred by Peter's comments. I think, yeah, there are all sorts of different definitions of explanation, and often it's, explaining what, to whom, why, and how. And all, if you tease all of those things apart, I think you get a sort of a richer, more general notion of explanation, and your characterization and Jillian's, I think, just fit into different versions of that. But with respect to Peter's comment about prediction, I think, you know, often embodied in these classifiers is this sort of closed world assumption.
I think did we lose Sheila? Okay, all right. So Mohammed, why don't we go to you, and then I'll come back to Sheila if she reads next.
Okay, thank you for the great talk, David. So I had actually two questions. One, I was thinking about, and this is really a follow-up, I guess, from your conversation also with Peter, about the definition of robustness based on these these explanations. Because if the classifier is really using that portion, that mask that you're finding, to make a good classification, then maybe it should just use that, right? That's like a minimalist definition for what the classifier should do. And I think it goes along with these two conditions that you had about removing a part and then removing the mask, or just giving it the mask. I think where those two meet is actually where such a robustness definition would actually be appropriate. So I'm really interested in that, like your thoughts about that. And my second question is on a higher level. I think explanation is intuitively, like at least to us human, is an interactive process. So you ask the model to explain something, and then you may not be satisfied with that. And then maybe there's an oracle that can tell you whether that explanation really, matches what you were expecting of it or not. Do you think there is a good way, with this being a Bayesian model somewhat, is there a good way to actually integrate that within your algorithm?
Wonderful question, thank you. So as for the first part, you were saying in terms of robustness, we want our image algorithms to only depend on like the actual bird or whatever, and not on like the background. And that's one of the ways we can tell whether it's going to generalize. And I agree. And I would say, you know, there's lots of work from like David Lopez Paz and people trying to avoid like spurious correlations. I think there's still an unsolved technical question, or unsolvable, which is, we don't like, if we just see a bunch of images of birds, classic examples like cows in the desert versus cows in a field, are the cows in the desert still cows? You know, there could be definitions of words that actually the answer does depend on the background, right? And we don't know. So I think we just have to keep both possibilities in mind. So I think this is a good diagnosis for robustness, but I don't think it addresses the problem in any strong way. I don't think we can. I guess I want to mention also Roger Gross has some awesome work on a sort of interactive, let's say, explanation. I think the other people have worked on it too. The debate game, where the idea is that you get to query some classifier and say like, well, you know, what if I only showed you these pixels or something like that? What would you say then? And interactively, they try to make a proof about how the decision was made. And so I'm not summarizing that work very well because I'm not very familiar with it, but I guess what I'm trying to say is I think there are people who have appreciated your point and actually formalized it already.
Great, thank you.
Thanks, Mohammed. Okay, Sheila, we're back to you. Hopefully we can hear you this time.
Yeah, we'll see whether, I'm going to leave my camera off. I have a sick child at home who's using the internet. So we'll see whether I lost it here. I'll try to turn on my camera. So I guess just two comments. I think the notion of just, you know, there's this Arthur whenever we eliminate the impossible, whatever's left, however improbable is likely what's true. I think there's this notion between refutation and prediction or confirmation. And I think maybe what David's getting at is more of this notion of refutation as opposed to confirmation. But when you have that you often have to, even though maybe everything, maybe a particular feature predicts all is strongly required for every single class, but you also want to know what discriminates between the classes, especially when you're building a classifier. So I'm not sure whether I'm giving enough detail to make sense, but there's this notion of sort of a closed world assumption with respect to a classifier, because you have a finite set of things and you have to choose one of the finite set of things. So if and that's different from an open world setting where you're just predicting things. And so I guess to Peter, I don't know that Peter's still here, but to Peter's point, I think prediction is not enough. I think this notion of counterfactual is important. The other thing I wanted to do to comment on is with respect to this, explaining what to whom, why, and how. Mayan Shvo, who's not here, and Torn Klassen, who was here before as well, have done some very nice work using theory of mind, where you really look at explanation in the context of who you're explaining something to. So different people or different agents have different belief states, and an explanation is something that you want to cause the recipient, the explanation is something that you give to the recipient that causes them to then be able to account for the thing that has prompted their question. So if they don't understand something and then you tell them something, that's an explanation to them, but maybe somebody else who has a different set of beliefs have to be told for the thing that they're trying to explain. And so I think this notion of who you're explaining things to, particularly when humans are in the loop, is a really important dimension of explanation. And I think that relates to some of Peter's comments as well. So that was all. I guess it's a statement rather than a question, but and you guys are sort of frozen, so maybe I'll stop there. But I don't know whether anybody else has any thoughts on that.
I was just going to say, I totally agree with you about the closed world assumption, and that's just one of the limitations we inherit from our models. And as for like it matters who you're giving the explanation to, I do think that the ultimate way to decide what we want when we want an explanation is just this boring answer of like, you have to average over all possible tasks or decisions that this person is going to have to do for the rest of their life, and then guess how much this information would help them in each setting, then give them that information. And it's kind of like a boring non-answer, but I guess I'm saying I think there's a limit to how far we can get by just arguing from definitions or like guessing at what the person might want to know. At some point, we have to actually just reason about future challenges they're going to face.
David, can I
agree with that.
Yeah, sorry, Sheila, I didn't mean to cut you in. Okay, so I actually want to dig into a bit more sort of the different purposes for which we want explanations. And what we mean by that, because I do think we use that term in a lot of different ways. So, let me just start off by asking, so when you think about the explanations you're generating, this part of the image is, like that's the most likely to change that's that counterfactual. So that was, pivotal in some sense in the classification. So what question do you think you're answering with that explanation? Who's using that explanation for what purpose? Is it, I guess I can run through my list of possible things, but I'm curious when you think about it, what's the value of having these explanations?
So I think it's a very weak or a very weird set of circumstances where that's exactly the question I care about. And maybe I can imagine if I was like trying to like point a telescope or like decide which image to show to a doctor, and I thought that I was equally a good doctor as them or something. Like the point is it's pretty contrived, and ultimately we do want to ask a different question about what intervention should we do on this patient or something like that. So I guess I want to say I don't want to defend these explanations as being particularly useful in general. The main point of my talk was just that whatever other type of explanation you actually care about, probably these counterfactuals will be important for answering it, and the generative models can help you with that.
Right. Okay. So that's then, so if you think that causal reasoning is actually part of what we're missing in a lot of our current approaches in AI, and that if to have systems that really do understand and can reason about the world, they need the capacity for causal reasoning. Are these methods that actually contribute to that sort of ratcheting up where we are on that, you know, what our AI can do?
Well, yeah. So the stuff that I did in my paper was not causal. It was just on the level of like correlations between pixels, and that's why I was pointing to later on the like causal version. So I guess what I'm trying to say is my thing was definitely missing a huge piece to be actually useful, which was expressing the counterfactuals in terms of like, what if we did this surgery, or what if we did this actual intervention that is available to us. Right.
Although that's specifically counterfactual. That's that treatment concept, right?
Yeah, I guess it's they're both counterfactual, I'd say. One is just though about an observation I could have made. The other one is about a intervention I could have made.
Mm-hmm. Right.
Thanks. I had not actually realized that until you just asked this question. This is awesome.
That's the point, right? That's the point of talking about this stuff. Yeah, so we've got any other questions? Dennis.
Well, thanks very much. I find this super fascinating. So I do philosophy of science, and some of these issues come up in that context. And I noticed that two of the things you were doing were kind of trying formally to distinguish between what we might call sensitivity to counterfactuals and robustness against counterfactual changes. So the idea there's certain things in the mask that if you were to take them out would really change things. So is that equivalent to asking a question you didn't ask explicitly, which is, what are the parts of the system such that were they not to be there, other changes would change the classification outcome quite radically? Or is that another question?
I think there's only the two, or at least in the image setting, the like sensitive region and the destructive region. There could be other ways of forming the question, but I think that there's only those two. And again, I would love to think about whether they're equivalent in some sense.
Okay, good, thanks.
David, can I just ask you another, so another issue that comes up once we start, so it's issues around explainable AI. So one is, we actually use these terms with different meanings. But the other is, you know, especially in your medical applications, you suggested that explanations would contribute to trust for doctors, and I think we have kind of mixed evidence on that, right? So we don't have Marzia here now, but I know that she's thought a lot about this. We've you know, I think we're kind of digging in, you know, what do we really know about what generates trust and what the relationship is between explanations and trust? I'm just curious if you know, are you thinking about that, or how do you?
Yeah, so I guess I'd say I hope that it can generate trust. I guess what I'll say is, we definitely are in the situation where there's the doctor and the machine. The doctor wants to learn about the machine to be able to reason about its decisions. And there's a very limited bandwidth channel between them. And the doctor can't just look at, you know, all the things the machine could have done, or all the information that the machine has seen in its life. So there has to be some way of bottlenecking this information. Whether my particular approach is the right way, I don't want to make any strong claims, but I do think it's an example of one way to formally reason about which information which would be most helpful to send from the one to the doctor.
Yeah. All right. Gosh, I have other questions here, but I don't want to dominate too much here. Any other thoughts from folks? Okay, I'll ask you the AI safety question. Are there applications of this to thinking about AI safety? Again, can I give you my three?
Yes,
who I think about? So I think about AI designers, people who are building AI. I think about the users, like the doctors. So there's you, there's the doctors, and then there's the people who are affected by it, the patients in the world, the subjects in the world. There's probably other groups too, and people should chime in if they think there are other groups we think about. And I think we actually want to distinguish, you know, like, you know, who are the explanations for? Are they for the folks building it, which is, I kind of think there's an AI safety component. Are they for the users who, you know, need to trust it, need to figure out how to use it, can learn from it? Or are we talking about, people affected by it. And that's where I think like the justification stories come in. And maybe there's a regulation story in there as well. But maybe my AI safety question is, if you're thinking about, I have the goal of only building systems that are safe, and I know how they're going to behave. Anyway, so AI safety.
Yeah, I think it's certainly realistic to think that all of this might only apply to the designers, and they can make themselves sure enough that it works, and then just like somehow force the doctors to use it. That's certainly a possibility. Yeah. Or some third party forces the doctors to use it because of cost or something.
Right. Okay. Sheila, go ahead, and then I'll go to Bipol.
Oh, I was just going to say, maybe it's suggestive of a way, people, when they build software, you typically unit test it. And maybe it's suggestive of a way to sort of systematize unit testing of a generative model and to make it safe in that way, sort of along more traditional software engineering, but with this as a piece of the building block.
Oh yeah, and
sorry, go ahead, David.
We did include some sanity checks in our paper. Like we know that this feature doesn't matter, so make sure that it doesn't get used. And there's like all these sorts of inequalities that that this should be more important than that. And so that is one nice thing. Great point, Sheila. Thank you.
Great. Hey, Paul.
Hey, so David, I wanted to ask about levels of explanation. I think Dennis also asked a similar question. So right now we are simply segmenting the image into two sections, one which is which is mainly responsible for the decision, and one which is the destruction region. What about levels of explanation? So say the images of children playing. So of course, one of the first things that would be available there for explanation is children. But assume we removed that children, those part of that image which represented children from there, but still toys and everything is there. So that is a second level of explanation that is present in the image. So will our model be segmenting the whole region in the first go, or will our model be able to first we identified this patch, then we remove that patch, then so the model will be able to identify another path. Basically imagine all the explanation patches are in a graph, and we are able to find the related nodes of that main explanation and develop some levels of explanation there. Will our model be able to do that?
I mean, I think so. I have a very unsatisfying answer, which is I don't think that we can say much about which types or levels of explanation will be most useful to a generic user without knowing more about them. So, I mean, so I'm saying great points, and I don't know how the machine could choose between those at this point.
But yeah, so right now we are simply creating two regions, right? And stopping there.
Well, I think the claim is that this region is sufficient to make the classifier confident, but it's not saying that the other regions are irrelevant. It's saying there could also be other regions that equally well would make the classifier confident. So we're not saying anything bad about the regions we didn't include. We're just saying we only needed this one.
Makes sense. Thanks.
All right. Thanks, you, Paul. Any other questions for David? Okay. Well, that's a wrap then. David, thank you so much for a really great talk. I think this is such a critical area of research and has so many directions to head in. So really great to hear about your work, and we'll keep following on that. Everyone, a reminder that our conference starts tomorrow with a graduate workshop, and then our sessions on Friday and Saturday. Lots of great things to find out about there. So if you should be on all our mailing lists, you should have Zoom links. Please reach out if you're missing those. And we are on Reading Week next week, so we won't have a talk next week on Wednesday, but we will the following one, which is November 17th. And our faculty affiliate, Chris Madison, talking about the future of representation learning. So we'll look forward to seeing you hopefully for the conference, and then 2 weeks time for that talk. Thanks, everybody. Have a good afternoon. Bye.